right, sorry for the rough start this morning. So Sophia came in, she mentioned that we'll be sending out those surveys. There's 2 surveys. I'll probably give, I think, 1 or 2 homework points apiece for those who complete it. And those are just surveys that sort of tell you about the study and then allow you to give consent. If you're not interested in participating in the study, that's fine. But we're just sort of interested in knowing whether setting up these retake schedules has a positive effect on learning outcomes, and we're sort of interested in more of the diversity. They're already studying a bunch of lower level biology courses, and so this is an opportunity for an upper level engineering course to see if there's any difference between the two. So we're interested in that, and if you like the retakes, then I can use studies like this to convince people of their efficacy, at least assuming it comes out positive. But it may come out and there's no difference whatsoever, and people say, it's too much work and I'm not going to do it. But if it does come up and showing a positive impact on scores, then we might be able to convince other people in other engineering courses to also take on similar retakes. So that's the idea there. Other announcements, so the videos for Lab 9 and 10 are available. So Lab 9 was this week, 10's next week. 10 has got sort of, it's graded out of 30 points, but it's a 50-point assignment. So you can do the first part of it, and then you've done a full lab. But if you really, want to delve into a little bit further, you can do the second part of it, and that's a potential for like 20 extra points. So it's like a 2/3 lab bolted onto a 1 lab. And so all that's available online. It's an opportunity to play a little bit more with Process Analyzer and OptQuest, at least for a little bit. It also introduces you to things like sequences and batching, which may be useful in your final project. Final project, nothing new to report here, just keep working on it. The next deliverable is the final week of classes when you present. Then there's an ICA, J3 is available, and there's one last ICA that's new before the final exam ICA. Homework J2 is out. It's the final homework assignment. It is an arena-based assignment, so it's going to feel a little bit more like a lab. You take a model that you've seen in lab before, the inventory model, the SS inventory optimization model, and actually go and do the optimization. So this is another place where it'll streamline this homework if you know how to use, say, the process analyzer at least, if not OptQuest, but you can also do it manually. Whereas all the other homeworks had a solution set that would be released with them, homework J2 won't because it's kind of an applied one, so we use it as an ABET metric, and so we can't distribute solution sets for things that we use as ABET metrics because there's too much similarity from semester to semester. So there won't be a solution to that, but it's really kind of more a practice assignment, so it's not like you're seeing, how do I do a chi-squared, where did I go wrong, that sort of thing. But I'm happy to answer any questions afterwards, like if you come to office hours or anything like that. So, question?
When will the input modeling reports be posted, like the grades?
I think about 1/3 of them have been posted, and now that I've finished these, I can go through and at least add my input, if not grades, but at least can give you guys feedback to see if everybody's on track. So hopefully, my aim is to have all those back to you by the end of the week.
Okay.
Any other questions? All right, so let's start with an attendance exercise just to get us thinking. So I'm just looking for a 1-word answer here, but just making it so that we're comfortable with these words. So the prompt here is it's about the t-test. So a student's t-test is what is more generally called a location test. And it assumes that data are normally distributed, and it only evaluates the probability of a particular location, which in the case of a normal distribution is the mean. So the question is because it evaluates the plausibility of a parameter and not a whole distribution. It assumes the distribution is taken for granted, and then it just says, is this parameter the right one? We call it a particular type of statistical test. What is the name that I'm looking for? What is the grouping of statistical tests that a t-test falls into? And I'm just looking for a 1- or 2-word answer. So because it makes an inference on a parameter, not a whole distribution, we call it a particular type of test. What is that? You guys can actually talk to your neighbors. Take 30 seconds and make sure that everybody's on the same page. and then we'll just see what the answer is together. All right, so what, does anybody have a good feeling, high confidence on an answer? Or low confidence, that's fine too. Yeah.
I said like a
Parametric test, that's what I'm looking for. So it's referred to it as a parametric test because it's a test which only focuses on the parameter. It has to be normally distributed going into it. So we take that for granted, and then we say, given that it's normally distributed, what's the right parameter? And you can say, I think the parameter is 2, and the t-test comes back and says it's very unlikely that it's 2. So that's why it's a parametric test. A non-parametric test doesn't make any assumptions, and then it's you're making a much broader claim, but you'll have less statistical power. Question?
So, like, since you're estimating the parameter in, like, you said it's a parametric test, like, would that be kind of like a point estimator kind of thing?
Well, that'll be what we get to kind of get in today. So we're not estimating a test doesn't estimate a parameter so much as evaluate whether a given parameter is a good one. So parameter estimation is what we're going to be talking about today, but a single t-test is more about, I really think the parameter should be 5. Based on these data, how likely is it that it's 5? Okay. All right, so there are a bunch of, so if I just look up location tests on Wikipedia, there's this nice table. And if you were to drill down into this table, it's basically a decision tree where they talk about, well, how many groups do you have? Is it normally distributed? Is it not? So, so basically it breaks up on, and there's kind of the leaves of this decision tree that's built this way. There's a bunch of parametric and non-parametric tests. And like I said, even though there's a bunch of these non-parametric tests that have funny names like Mann-Whitney U-test, if I were to just Google for non-parametric t-test, then I would end up finding it. So like here I see under 2 groups that are independent. If they're normally distributed, I do a t-test. If they're not normally distributed, there it is, a Mann-Whitney U-test. So any insight that you have, we usually teach you guys parametric tests first. And so you usually say, yeah, I kind of get a conceptual model of statistics through things like t-tests and ANOVAs. But then when we throw in real data at you and it's not normally distributed, it feels like you have to learn a whole bunch of other tests. But they all kind of function the same way. So focus less on the test and more about the assumptions. And if you were just to Google for what's a t-test I can use with non-normally distributed data, or what's a non-parametric ANOVA, then the first line in a Google search result will be the right test 99% of the time. So, so that's, over time, you'll develop this tree in your head, but in the short term, just simply taking your parametric stuff and bolting on non-parametric. If you do a search for that, there's a bunch of resources that'll say, oh, you wanted to do a t-test, but you couldn't, we'll do a u-test instead. You want to do an ANOVA, we'll do a Kruskal-Wallis, et cetera, et cetera. So I'm not going to force you to learn this decision tree, but there are several that I do want you to at least start to baking into your initial decision tree, like the Shapiro-Wilk. What's the Shapiro-Wilk test for? What's the one thing we use Shapiro-Wilk for? Take 30 seconds and talk to your neighbor. What is the Shapiro-Wilk test for? All right, let's bring it back together. So what is the one function of Shapiro-Wilk? Does anybody remember? Yeah. Test for normality. It is a goodness of fit test for normality. So whenever you want to use a parametric test because you think it's good that it has high statistical power, first thing you do is run a QQ plot. See, does this look normally distributed? If it falls on a line on a QQ plot, then the next thing you do is go into your statistical tool, up to the tools menu, and look for Shapiro-Wilk test. Shapiro-Wilk test comes out. It says it's got a p-value of 0.4. Great. The Shapiro-Wilk did not reject normality. It looks normal on a QQ plot. I can proceed with my t-test. If Shapiro-Wilk pops out and it rejects it, or if your QQ plot does not look like a line, then in that case you might be out of luck. You either need to transform your data to make it normal, or just go ahead and use like a U-test. Yeah.
So, like, could you repeat that? Like, you just said if like it looks like a line, then it's normal. The QQ.
In a QQ plot where the hypothesis is normal, if your data ends up falling on a line consistent with the hypothesis, then the QQ plot provides evidence it's normal.
Okay.
And then after that, to get quantitative evidence, then you run the Shapiro-Wilk. And if it comes out and does not reject the normal, then you can move forward with the parametric test. All right. You have any other questions about that? And we're done with talking about statistical tests for today, specific ones at least, and we focus more on point and interval estimation in these terminating simulations. All right, so the main focus of this unit, so these four, last lecture, this lecture, and 2 more next week, is what measures should we be making decisions on in SIMs, and what are the different strategies for terminating and non-terminating systems, as well as estimating absolute and relative performance. And so how do we end up building SIMs that don't take a whole lot of time, but they have enough statistical power for us to make interesting conclusions? So if we had enough computational time, we just run lots and lots of replications. But because we don't, we have to run a limited number of replications. So how many do we run in order to make a good inference? And then the other thing is that if I have these non-terminating simulations where I'm interested in steady state values, then bias is a major issue. So again, I have a computational time and bias reduction problem. If I run the sim for a long amount of time, I will get rid of my bias. But if I do that, the sim is going to take a long amount of time. So what strategies can I do to get rid of the bias without having to run the sims for a huge amount of time? And that's what we'll be covering coming up actually sort of the next lecture. So this lecture, we're sort of focusing on this part here. So last time we introduced terminating and non-terminating systems. You guys came up with some examples of these. Just the kind of nutshell was that in a terminating system, we actually care about the entire transient from the initial condition of the sim to some final condition, and we include this transient in our statistical estimations. And so this estimate of performance is influenced by both the transient and this sort of steady state value, but that we want that, and so this is not an indicator of bias. But in the non-terminating case, this is just an artifact of our simulation having to start somewhere. It's an initial value problem, like in calculus. It has to start somewhere. And so I'm going to get a transient, but then it's going to settle out at some steady state value. If I care about the steady state value, I don't want to include this. It pulls that estimate down. So if I do include it, then I get this estimated value down here, which has got a gap between what I wanted. And that gap is what we refer to as bias. And I'll define that more formally, mathematically in a second. But the basic idea here is I need to then establish a warm-up period, which you'll do in Lab 9. And that warm-up period is of throwing away these transients so that my steady state estimates get rid of this bias. And so that's sort of, in a nutshell, of the kind of the major difference here in both the types of systems and the way in which we'll handle the data. So this bias that I mentioned formally, basically any data that I want to estimate theta, which is just some performance parameter. That might be the question?
Yeah, good question. If you were testing for causation, then that means you would not use a steady state simulation, right?
Well, I guess I don't know what you mean by it. So if you test for, so when we say testing for causation, that usually the only way we can make a clear inference about causation is by making an intervention. So, and we still could have interventional ways of studying non-terminating systems. So for example, I could say, I don't know, but I think the placement of that door is affecting the steady state traffic flow into and out of the building or something like that. And so based on that hypothesis, then the prediction would be if I move the door, then I should get a different steady state traffic flow. So, and if I move it and I don't, then that maybe indicates that even if there might be a correlation, that the door isn't actually participating causally in that. So that would be a case where I would use a steady state simulation to get at causation. So if, but if you're, I guess maybe the point you're getting at is if in a terminating one, if I was interested in sort of following over a time series, then I might say, well, if I want to perturb this sometime in the virtual world, what would the transients look like? Then yeah, that would be something you could study here. But I guess I'm not ready to make a blanket statement that this is where we study causal relationships and this is where we don't. They're just different ways of testing hypotheses. Okay, so this parameter theta, this is our generic way of saying something we want to estimate, like the mean number of customers waiting in a line, the mean wait time for each particular customer. It's something that is going to be variable whenever I measure from my simulation. And so I'm going to take samples, and I'm probably going to have to average those samples or do something with the aggregate of those samples. That aggregate will itself be a random variable. So, and that itself is going to have a distribution. So if I know that the actual mean of a population is mu, but I can't ever observe mu, I can just observe samples from the population. So I get a sample y1, a sample y2, a sample y3. I might say, well, I'm going to add all those up, and I'll get some y bar, which is my estimate of this mean parameter. But if I were to rerun this experiment over and over again, so I get another y1, another y2, another y3, and then get another y bar, every y bar I get every time I rerun this experiment is going to have some variability. So just as y is a random variable, then so is y bar. And so since it's a random variable, then it has an expected value. And so I can ask, any estimation technique that I do, what's the distribution of values I get out of the estimator? And does the mean of the estimator coincide with the real mean from the population? And so that's where we get this term bias, is that if I subtract the mean of my estimator minus the real mean of the real system, so this, like my simulator itself could be part of the estimator and the real system could be out in the real world. And this gap is what we call bias. And so if there's positive bias, then that means I'm estimating something that's higher than the real one. If there's negative, it's the other way around. Ideally, I build an estimator where my estimator's mean is going to be equal to the real world mean. And that's a nice effective estimator. And this is something we refer to as an unbiased estimator. But it is really hard to build an unbiased estimator. And sometimes, if you really care about reducing the variance of your estimator, remember, if an estimator is a random variable, it's got variance too. Sometimes, due to bias-variance trade-offs, you actually tolerate a little bit of bias because you want less variance. And there are cases where we're studying relative performance where we actually don't really care if the estimator is biased, just so long as it gives us consistent results. And we've got another estimator that gives us consistent results, and we can compare the two of them. So, so there are times in which you will tolerate a certain amount of bias. But ideally, you've got no bias, which means that your estimator is going to give you mean values that will cluster around the actual mean. So that's what we mean by bias, and that's why in this picture, I'm labeling this as bias, because what we've done is we've aggregated over samples over the entire run. And that aggregation ends up moving the estimate of this steady state value down. And so the real steady state value is up here, the estimated value is down here, and so we get negative bias. So any questions about this term bias and our formal definition of what we mean by a biased estimator? The two key components is that estimators are variable, so they have means, and the bias is the difference between the estimator's variance and the real system's variance, or the estimator's mean and the real system's mean. Okay. So this was the example I gave, just blown up here, so I forgot that I could go forward and I went back, but this is exactly what I was just saying here, that if I'm trying to estimate this steady state value and I use data from here, my estimate will be pulled down and I get negative bias then. All right, so then the major estimators that we'll use are typically going to be arithmetic means and these continuous time means. So if I have data that comes from a list, I just take an arithmetic mean across the list, and that's the common estimator that I'll use. If I have data that come from a time series where it's defined at every single time, these are so-called time persistent data, then I might take the integral underneath that curve and then divide it by the total time interval. And so every time I use the term time average, I'm referring to this integral. And then if I just refer to normal average, then I'm referring to this sum. So there's those two there. And so the two examples here is I might say, well, on the discrete side, I might have a 1 or a 0 if my stock is out or not. So do I have stock in an inventory, or am I totally out of stock? And then that thing fluctuates over time. And so, but I might say like, well, every day I might just take that measurement. So that might go into, what is, on average, what fraction of days am I out of stock? Well, that would be this guy. But alternatively, I could say, well, the length of a queue. Well, I can ask at every instant of time what the length of a queue is. And so this is a time persistent measurement. And then I might then want to take a time average. And so for every instant of time, I know how long that, or maybe if the queue is greater than 10, but then I want to say, what is the time average for how much time, what fraction of time do I spend with the queue being longer than 10? So this is a fraction of an interval of time, and this is sort of a fraction of a set of days. So those are the two differences there. Time average versus normal average. Any questions about those definitions? Hopefully they seem pretty straightforward. And I'll show you in Arena how you can define tallies and time persistent and then end up calculating these things out of your Arena sim. The other thing that we'll estimate are quantiles. And quantiles are just the flip side of CDFs. And so if quantile describes a level that can dominate a certain specified fraction of your outputs. And so I generate a sim, I run that sim 1,000 times, and it gives me a bunch of different values every time I run it. And I'm interested in knowing what's the 85th percentile. At what value am I greater than exactly 85% of my simulations? And so that's defined this way, where this looks like a CDF, but the weird thing is I'm putting the input in here. I'm saying what is the value theta that makes the CDF equal to whatever my percentile is. And that's where we get the quantile function is the inverse CDF. It's just the inverse of this thing here. The way I get quantiles is I just sort all of the data out of my sims, and then I just ask, well, if I want to know the 85th percentile, I just then look at 85% of the data, and I take the top one. And so that's all we're saying here is that the P quantile is the value, the actual sample that is in the rank, which is whatever my quantile is, 85% times my number of samples. I round that up, and then this gives me the rank of my quantile. So and so in a histogram, this will be the line that will be to the right of 85% of the data. So as an example of that, so let's think about hypothesis testing. You can use a simulation to generate a test statistic. And so what I mean by that is we've talked about this blue curve. This is your test distribution. So, in t-test, we've solved for this mathematically. Well, sometimes it's difficult to know what test statistic you want, but you know that your simulation is as much of a null model as some mathematical notion that went into a t-test. And so you might want to say, based on the data I've seen, can I use a simulation to generate this statistic? And so here's an example here. Imagine if a fire alarm goes off in a museum, a bunch of people come out of the museum, there's 1 or 2 people that come out really late, and they know that afterwards something was stolen in the museum, and they're interested in who is a person of interest. And they say, well, these people that came out late, they had more time. And so maybe they did something that ended up resulting in being part of the burglary. So then the question is, but then those people come out and they say, no, you know what, I heard the alarm and I just went a little slower than usual and I wasn't quite sure where I was going, and so I took a longer path. And so what I can do is, what I did is I built a little simulation where I ran it a whole bunch of times, where I had my simulated entities end up deciding on random speeds and random distances between them and the exit. And so I have a distribution of distances and I have a distribution of speeds, and I can then say that if they really were just trying to get out, but some of them were slow and some of them took longer distances, I can say together what was the distribution of times that I would expect someone in exiting the museum. And it might look like something funny like this. And this is saying that most people left in this time, but there was a tail, and so there were some people in my sim that took this amount of time to get out of the museum. And so I can then set a critical value, which is just the 95th percentile. So when I say I want an alpha, a false positive rate of 5%, all I'm saying is that I want 95% of the outcomes to be on this side of the threshold. And so that's just me estimating a quantile from the data. I have a whole bunch of these things. I'm going to sort them, and then I'm going to then find the value which dominates 95% of all the other values. And that becomes my threshold. Now, my person of interest, they left the museum at this time. And I can say, well, that's in this tail. Your story is plausible, but it is highly unlikely. And so we're going to bring you downtown because you're now a person of interest. But somebody over here, then they'd say, well, you know what, we only want a false positive rate of 5%. If it took them this long to get out of the museum, then maybe they're not willing, and we won't call them a person of interest. So this is an example of how you can use numerical methods and computational methods as statistical distribution generators, and then use them to build your own hypothesis test based on a null model that would be difficult to formulate mathematically, but is easy to formulate as a sim. So there are questions about that. Does it make sense how I built a null model of a museum? This is a null model of escape behavior in a museum. And I'm testing against the alternative hypothesis that someone hung around to rip some paintings off the wall and stow them away somewhere where they could pick them up later. So my alternative hypothesis might have a distribution that's over here, and I have no idea what that distribution's like. But my null, which is my okay reasons for leaving the museum, has a distribution that looks like this. And so if I get a measurement and it's sitting over here, it is unlikely to come from my null. So I have to assume there were alternative reasons that they were staying in the museum that long. Questions about that? And then the lesson here regarding quantile estimation, I just sorted all of my simulation outcomes, and I took the one that was dominated 95% of all the others, and I got the 95th percentile, and that 95th percentile is effectively a test statistic that I used to do this hypothesis test. Okay. So now, what we didn't get to last time was then interval estimation. And so interval estimation, from here on out, we're going to we're not going to talk about point estimators very often unless they also have half-widths around them, because intervals end up being much more honest and much more useful estimates that come out of simulations. And so the idea is I have my point estimator for mean, and I want to define in some useful way an interval that goes back a little bit and forward a little bit that sort of captures how confident I am that my mean is real. So my estimator is going to come out, and I will have a certain confidence interval around this y bar. And the question is, how do I adjust the size of this to tell you how confident I am that the real mean is actually in this interval? And that's what a confidence interval does, is that a confidence interval is a visualization of a t-test. The confidence interval is all of the hypotheses that could not be rejected by a t-test. And so that's why in the definition for half-width down here, you see that critical t value. So this is saying that you estimated the mean, the point estimate here. How many, so we know that you probably can't reject the hypothesis that you're right dead on. You've got the population mean really might be your point estimate. You can't reject that. How many other hypotheses can you also not reject? And that is captured by this half-width. So if I go a little bit over, that's a hypothesis that I probably won't reject. But if I go way outside the half-width, so if I land outside here, then I can be pretty sure that if this is a 95% confidence interval, then this value out here will have a p-value of less than 5%. So that's the notion of confidence intervals there. Does that make sense? That a confidence interval is just the it's the interval of hypotheses impossible to be rejected by a t-test for these data at that level. question.
So confidence intervals and half widths are the same thing.
A half width is half of a confidence interval. So, yeah, so I defined the formula for half width, but then the confidence interval goes backwards and forwards by the half width. So the interval is both directions, centered on the mean. So, yeah, any questions about that? Does that make sense? Yeah.
For example, I mean, like we have, like been using like the t-test for when we don't know population parameters, but like, can you give me an example of like when you would for sure know the population and not the simple parameters?
Well, that wasn't the example I was trying to set up. So it's not that I'm saying I know the population parameter, but the question is like, how do I run? I have a bunch of data, and in some ways I can say, are these data consistent with one hypothetical parameter? And that's what a t-test does. But very often your stakeholders don't have an idea of what the population parameter is. They would rather know what are the hypothetical parameters that you can't reject with these data. So I don't know, I don't have one that I want you to test. I want you to tell me, if I did come up with one, how would it test? So how can I summarize every single hypothesis that could not be rejected? And that's what the confidence interval is about. Based on the amount of data that I've gathered, I can reject everything outside of the confidence interval. So if I were to draw this real line, so this is all my real numbers, and I happen to gather data. So I have a bunch of data, and I end up generating this confidence interval. And let's say it's a 95% confidence interval. So that'll be centered on my point estimate, and it'll have a half width on both sides that comes out of this formula. And so this is just saying that once I give you the confidence interval, then without doing a t-test, you can immediately evaluate t-tests. So you can say, what would happen with a t-test if this was my hypothetical distribution? This was my mu naught. And I would say, well, for there, the p-value is going to be less than 0.05 because it's outside the confidence interval. If I happen to pick one that's inside the confidence interval for that, then I know that my p-value is going to be greater than 0.05. So basically what this is saying, another way people like to talk about confidence intervals, and this is what I sort of say here, is that the confidence, 95%, that doesn't say 95% of the data fall into there. That means that if I drew 100 confidence intervals, I ran the experiment 100 times, and every time I generated a new confidence interval, 95 of those intervals would capture the true mean. And so because of that, then another way to say that is if you give me a hypothetical option for a parameter, if it falls outside the confidence interval, then there's a less than 5% chance that we will be wrong by saying that that is not the mean. So I can't tell you anything about things inside here. I have no idea what the status of these are. These might be good, these might be bad, but all I can tell you is that the p-value is greater than 0.05. But outside here, these are all bad, at least at the 95% level. I'm willing to take the 5% chance and say that all of these and these are bad, but I can't say anything about anything in between. That's what a confidence interval is. And what's beautiful to me about confidence intervals is that before you took a stats class, I am sure that you've heard of confidence intervals. There are news reporters, and they talk about confidence intervals. They're so easy for people to talk about. And yet t-tests are not only kind of boring, but they're just kind of abstract and they're weird, and nobody really understands what a t-test is, until you take a couple of stats classes. But everybody has some intuition about what a confidence interval is. And they're the same thing. Whenever you represent data as a confidence interval, you just did a t-test, but you didn't have to call it a t-test. That's the reason why we're going to move on with interval estimation for the rest of the semester, because this is far more marketable. This is so much more easy to communicate than a t-test to all of our stakeholders, because they will understand, at least to some extent, what a confidence interval is, but they will not understand what a p-value from a t-test is. But they're identical. They are identical. All right, so if I give you a confidence interval, I am implicitly giving you a mean estimate and a standard deviation estimate. And so you can calculate from one to the other. And you'll have to do this in your labs and in your homeworks. So the idea is if I give you a confidence interval like this one, you should be able to calculate a half-width, and if you know the number of samples, you should be able to back out the standard deviation. So if and you end up with a formula like this one. So you just solve this for S, and you get this thing right here. So basically, I can summarize a distribution for you just by giving you its confidence interval. And then if I give you a 95% confidence interval, you can come back and recalculate the 90% confidence interval, because you just can back out the standard deviation, and then you can recalculate the half-width for the different confidence level. So you can go back and forth between these pretty easily. So even though ARENA only gives you 95% confidence intervals in the reports, if the reports are working for you, the output analyzer allows you to choose anything you want. But in the reports, you might be stuck at 95%, but that's okay, because if you know how many samples went into the calculation, you can then calculate whatever confidence interval you want, 90%, 99%, etc. And you can also then, because we're assuming normality, because you can only use confidence intervals if your data are assumed to be normal, because they're t-tests. Confidence intervals are t-tests. So all of the assumptions for t-tests also apply to confidence intervals. So if I give you a confidence interval, you can actually tell me the two parameters for the normal distribution that captures all the data. And that means you can estimate quantiles, you can estimate the whole distribution. So we'll see that here in a second. Now here is a shortcut for two sample t-tests. So this here is a shortcut for one sample t-test. If it's outside of the confidence interval, reject it. Now, two sample t-test, I can calculate a confidence interval for both populations. And then the question, if those do not overlap, if they are mutually exclusive, then I know that I will reject the hypothesis of their means being equal with the appropriate, with p less than 0.05 in the case of a 95% confidence interval. So I can visually, and I'll show an example of this in a second, show you confidence intervals on a graph. And without you doing any math, you'll be able to evaluate the outcome of a two-sample t-test. Now, a lot of times people will plot error bars that have standard error and not confidence intervals. And if you know that those data are normal and someone's giving you the standard error, a really convenient thing is that the t-statistic value that scales down here, notice this is just standard error in the formula, and this is just a scalar out front. That t-statistic, that critical t-statistic value, as your number of samples gets higher, it approaches 2. It actually approaches 1.96. But we can approximate it as 2. So if somebody gives you standard error bars, you can visually double them and then evaluate, does that doubled version intersect with other doubled versions? And if they still are mutually exclusive, if they do not intersect, then you can conclude that your two-sample t-test says that these are different populations. So here's an example of what I mean. So here is, these are data, I think this is actually from a real paper, where they've had a control treatment, and then they actually have a treatment. So this is, I think, pharmaceutical data, and they were studying enzyme activity as their response variable. And so they plotted the control with standard error bars. So you notice SEM. They then plotted the treatment with standard error bars. Now, initially, when you look at this, if you're not statistically minded, you see that these error bars do not, there's daylight between them. I could put a horizontal line in between these two, and you might say that indicates to me that there's an effect of the treatment. But you have to remember that you can only do this two-sample t-test with confidence intervals. If I double these standard error bars so that they come out this much farther down and this much farther up, then I see that these intervals actually now intersect. And when they intersect, I actually have to go through the math and do a real two-sample t-test. But if you go into, say, the output analyzer, and you can have it plot confidence intervals, if you notice that the confidence intervals are far apart, they kind of look like this, you can immediately conclude, without even looking at the numbers, that the two-sample t-test is significant, and these two populations are different. Are there questions about that? So you see what I mean, that if I give you standard error bars, you double them, and you get confidence intervals. And then you can use this rule of thumb, or whatever you want to call it, that says that if the two confidence intervals do not overlap, you know the outcome of the t-test without even doing the t-test. All right, so let's do another attendance question based on that then. So let's say I give you this plot. You can talk to your neighbors, take 30 seconds and chat about your answer. But let's say I gave you, this is the same plot as before, but now I'm actually telling you that these bars, let's just assume that they are 90%, not 95, 90% confidence intervals. So given that they do not overlap, and I'm telling you that they are 90% confidence intervals, without even calculating anything, what do I know about the p-value? So tell me with as much certainty as possible what you know about the value of the p-value if you were to do a two-sample t-test, given these are 90% confidence intervals. So chat about that with your neighbor, and your answer for your p-value will be the attendance thing. We'll bring it back in chat. All right, so let's bring it back and do a little survey of what people think here. So based on your discussions with each other, how many people would vote for that the most that you can say is nothing, that the p-value could be anything? I can't tell any information whatsoever from this graph. All right, how many people would say, I do know something about the p-value, and it's between 0 and 0.05? All right, how many people would say, I do know something about the p-value, and it's between 0 and 0.1? Right, we're going to start to get some hands up there. How many people would say, I do know something about the p-value, and it's greater than 0.05? Okay, there's some hands there. How many people would say, I do know something about the p-value, and it's greater than 0.1? I have a couple of hands there. So if I were to sort of summarize, it looked like nobody voted for this, I thought. Nobody voted for this. There were, we'll say, a large number for this, a moderate number for this, and a small number for this. So it's kind of our frequency distribution for these here. And so the answer that I would say is that all that we can say for sure is this. It's between 0 and 0.1. We can't say for sure that it's greater than 0.05. It might still be less than 0.05. But based on this graphical analysis, I'm only sort of given enough information to evaluate the confidence level for effectively alpha equal to 0.1. And that's where this 0.1 comes from. 1 minus the confidence value gives you alpha. And so I also can't say it's greater than 0.1 because I know that if it were that when they're not overlapping, I know that it's a significant result. A significant result means it is less than alpha. And so the p-value will be less than 0.1. So that, to me, is what I would conclude from these data if you were to show these data to me. Are there questions about that? All right, good. Okay, so given that I give you a confidence interval, we can estimate a whole lot about it because confidence intervals necessarily mean the data are normally distributed because you can't use a confidence interval if your data haven't already been shown to be normal. So again, confidence intervals, t-tests, all the same restrictions. So if I give you a confidence interval, so I gave you one and it has a lower bound and an upper bound, I can estimate the mean, that's just the average of the two. I can estimate the half width, it's just half of the width of the interval. And then with the half width, I can estimate the standard deviation of the distribution using that formula, where R is the number of samples that were used there. So given all of that, given that I know that it's a normal distribution is fully characterized by mean and standard deviation. So once I have an estimate for mean and standard deviation, I actually know the entire distribution shape. And I can estimate it to have this mean and that standard deviation. And so if I want to know a quantile, well, I basically sort of just turn to my z-scores. As I say, well, if I want to know, so we'll do quantile down here, maybe I'll start with this one. If I have a particular outcome, and I'd like to see, like, say, the CDF, well, I know that all I need to do is look at the CDF of a standard normal. So I take the outcome, I calculate its z-score using these two parameters, and then I ask, where is that z-score in terms of the standard normal CDF? And that will be an approximation for the CDF for my distribution. Or if I want to go the other way around and get quantiles, I can say, well, if I want the 95th percentile, I look up in a table and I figure out what the critical value is for the 95th percentile. I scale it by my standard deviation, I shift it by my mean, and then that will give me my 95th percentile. So just with a confidence interval, I get a whole lot of estimation ability out of that. So I've effectively done an input model. Yeah.
Is the capital R just
Oh, I'm sorry. Capital R is just number of replications. So in these, when we talk about sims, sometimes we use capital R for the number of replications because we'll often use n to represent the number of things within a replication. So little n will be within a replication and capital R will be across. I'm sorry, I didn't define that there. All right, and then the other thing that I can do is I say, well, what if somebody asks for the 95th percent confidence, or they want to know the 95th percentile, but I want to show them that I'm not quite sure. So how do I build a confidence interval around a quantile estimation? So I can make a point estimate of my quantile. So they ask for the 95th percentile. Well, it turns out that I can plug that into this formula, and this gives me a point estimate of the 95th percentile. But then I can actually put a confidence interval around that. And there's just a formula here where this defines the half width around the quantile. So I've done an example here. So I give you a bunch of data that's down here, and I've sorted it so that its rankings are below the data, and someone wants to know what the 80th quantile is with a 95% confidence interval. So I've got two percentages that are working together there. It's the 0.8 quantile, the 80th percentile, but I want the 95th confidence interval around that quantile estimate. So I sort the data, I take a point estimate for where I think the 0.8 quantile is, the 80th percentile, and that is just whatever the number of samples are times 0.8, so it's going to be at the 800th rank. And then I end up use that formula to calculate my two half widths, or my one half width. I go down a certain amount and over a certain amount. So I started at 0.8, and so this is going to tell me that I need to go to whatever ranking is at 78%, and this is going to tell me I need to go over to whatever ranking is 82%. So if I look at my sorted data, there's my point estimate, which is 80% of the data, and then I go over to 78% of the data, that gives me my lower bound. I go over to 82% of the data, that gives me my upper bound, and then so my confidence interval, my 95th percentile confidence interval around the 80th percentile, or the 0.8 quantile is this interval. It's somewhere between 188.96 and 256.79 for this data set. Yeah.
So I don't get practically why you care about those quantiles.
Why do I? So as an example, let's say you're simulating a traffic scenario, and you would like to see how adding enforcement affects the distribution of speeds on the road. Now, a lot of people don't realize this, but the speed limit is designed to be the 85th percentile speed. It is not designed to be the upper limit. They know that some people won't comply. And so given that they won't comply, then they say, well, where do we put it to sort of ensure that at least 85% of the people comply? If you end up taking data and you find out from your real data that 50% of the people are going faster than the speed limit, then you know you need to add enforcement. So you might build a sim where you add enforcement, and you need to see how much enforcement do I need to add in order to bring my 85th percentile down. Now the sim is going to be variable, and so that's why I need this interval estimation. But I'd like to estimate what is the 85th percentile speed. So I might have 4 different sims, one with like draconian levels of enforcement, where there's lasers just shooting people out of the sky that whenever they go a little bit over. And at that point, I probably get 100% of people under the speed limit. But I might have on the other end where I just totally lift all the cops out of there, and maybe people, they don't even pay any attention. So then, everybody is above, or maybe it's median or something like that. And I end up finding that, okay, well, maybe if I put a cop on the intersection only at these hours of the day, and then look at my distribution of speeds, then the output for my sim, its 85th percentile will end up being at my speed limit, and that then is what I'm going to recommend the cops do. Does that make sense? Questions?
So basically estimating quantiles just means like calculating constant intervals.
So there's 2 different concepts here. So the quantile is a point estimator of a distribution. It's like estimating the median, as the 50th percentile. So, but it's like a more generalized version of that. I want to estimate where is 80% of my data. But for the same reasons as the mean has variability when I estimate it, the estimate of the 80th percentile is going to have variance. And so I then need to capture the variance in my quantile estimate, and that's why I have a confidence interval around the quantile estimate. And it's a mouthful because you've got the 80th percentile and the 95th percentile confidence interval together, which is why you usually don't say all of that. You just give people an interval. And if somebody sees an interval, they know that it's probably the 95th percentile interval. Yeah.
So quantile is just the same as point estimator?
It is a type of point estimator. And instead of estimating the mean, I'm estimating the quantile. So I'm estimating in here the 0.8 quantile or the 80th percentile. All right. Okay, so now the last interval that you should be familiar with is the prediction interval. And so if I take a bunch of data out of a sim, the question is, I mentioned that a lot of people misunderstand the confidence interval, and they say the 95th percentile confidence interval is where 95% of the data are. And that is not the case. It's a confidence interval is where your estimate of the mean is. How far away from Y bar can you get before you start saying that these means are far too far away? Now, a prediction interval is what most people think a confidence interval is. And a prediction interval is where 95% of the data are. So, but if I only run a couple of sims, I'm going to have my prediction interval is going to have not only the actual variance in the system, but it's going to have additional variance from the uncertainty of only running a few sims. So your prediction interval is initially gigantic, but then over time, as you take more data, it collapses, but it doesn't collapse all the way to 0. It collapses to a normal distribution. And that normal distribution is an estimate of where all of your data lie. So if somebody says, so whereas a confidence interval is about it's about error, it's how far away is my estimate of a point. A prediction interval is about risk. Given the data that I've taken so far from my sim, if I ran the sim again, what's the probability that I would get an outcome that would be far away from the data that I've already seen? And so that's what the prediction interval is about. Clear the difference between PI and CI. PI is what most people outside these walls think is a CI. Okay. All right, so let's then see how ARENA does this stuff. We've actually sort of already covered the important thing I need to cover out of here in the half-width discussion, since I just pulled those slides in. But so I mentioned that in ARENA, if you want to get your data out of ARENA, if you're uncomfortable with any of the ARENA tools, you can use these read-write blocks, and they allow you to just dump the raw data right out to files, and you can do your own analysis. And so I've got a video on Canvas that shows you how to use these read-write modules. Basically, an entity goes in, and then it writes a line out to a CSV file, and that line can have a whole bunch of columns in it and capture a bunch of data. And so that is one way that you can get data out, so long as you're okay with all that data being triggered by entities running through this module. The other way is to use these record blocks. And so you can open up these record blocks, and you'll be doing this in the labs and in the next homeworks, where you end up being able to choose a bunch of different things that, again, when an entity goes through, that Arena will keep in its internal memory. And then in the reports, it will do the summary statistics for you. Or in the output analyzer, you can then pick off these things and say, show me the confidence interval for that. Compare these two things, et cetera, et cetera. And the types of things that you can record in a record module are tallies and counters. A tally is, for a single replication, is a list of things. So you want to run one rep, and you get a bunch of data out. And so I could calculate the time interval between entities. Well, since there's multiple entities, there were multiple time intervals in between, and this will capture all of them. And I can capture the time between. I can capture any expression that I want. Whenever an entity goes through there, I want to grab some piece of data, so I run an expression that maybe it's got some mathematics in it, and it saves it into a tally. And then that list, I can either dump the whole list into the output analyzer, or I can then just grab at the end of my replication the mean of that list, or the max of that list, etc. The other thing that I can grab is an accounter, which is just an internal piece of memory in Arena that increments or decrements by an amount that you specify whenever an entity goes through the record block. And so that's not a list, but it's constantly being updated, and at the end of the sim, you can just dump out that counter. So then how do I get those data out? If you go in the advanced panel, or advanced process panel, there is a statistic block that you'll use in the lab. And inside that statistic block, it'll be empty down here in the spreadsheet view, and you can add statistics to this. And each one of these things, Arena will keep track of in your reports, and it will also make them accessible to the process analyzer, the output analyzer, and OptQuest. And so you can go into here, and it's got a bunch of different types. And so I'll mention the different types that you can select in here. Are either, you can actually dump out tallies or counters, or you can say, I want to create a new type called time persistent. And this grabs one of those continuous waveforms, like the length of the queue at a particular instant. And then you can run in an expression here, something that aggregates, does like a time average. So I can say, what is the maximum value of that time persistent expression? What is the average, the time average of that time persistent expression, etc. So you can dump either the whole time persistent data out, or you can build an output expression that ends up doing those averages for you, so you get one data point per replication. And then there's frequency statistics, where you can actually then set up the different classes, and Arena will count whenever an entity falls into those classes. And then instead of giving you all of the entities out, it will just give you the counts of those. And so it gives you a discrete distribution across the classes that you define inside the statistic. So all of those things that you define inside here, which will show up one per row, will show up in your reports. So if I go to reports and I go to user defined, then I end up finding all of those statistics here, and it'll give me summary statistics. It'll give me whatever seems appropriate for that type of data. So I can get my means, I can get my confidence intervals and everything right out of the reports. The other thing that I can do is I can export those summary statistics to CSV. So if Crystal Reports isn't working for you, then you can go to Tools, Export Summary Statistics, and all of this per replication data under category by replication here will get dumped out into a CSV file that looks like this one. So every column is a replication, and every row is one of those different statistics. And so then you can generate your own category overview by, say, taking the mean across here, taking the confidence interval across here, and so on. So this is another way you can manually do it. The other thing that we would do is we can go into the statistic, and we can, under output file, and this is what you'll do in the lab, put in a file name there, and that DAT file that you put in there can be loaded into the output analyzer. And so I've got a video online that talks about the output analyzer, but basically the output analyzer has a bunch of things like graph that can preview these data from here. It also allows you to do things like calculate confidence intervals. So if you're not confident in calculating a confidence interval in Excel yourself, you can go into here and say, give me a confidence interval on mean, classical, bring in that data file, and it'll dump out a confidence interval. It can also compare means. It'll do the t-test and things like that for you. So here's how it calculates confidence interval. I grab some data from a sim called total cost, It shows me visually where the confidence interval is. It's hard for you guys to see, but it's basically showing me a real line. So I know that anything outside of this confidence interval would be rejected. And then it summarizes the half-width of the confidence interval and so on down here. If I have two data sets that I want to compare, I can go into compare means, and I can set a confidence level, and I can say whether to do a paired t-test or a two-sample t-test, and it'll do all the stats for you and just output a p-value, and it'll show you confidence intervals summarizing the result. It also will do a one-way ANOVA. I can load in all my different factor levels, and then it'll compare across those factor levels, and it'll even do a post hoc test. So it says comparison method, and I selected Bonferroni because we've seen that before, but you can select Tukey or some of the other methods in there, and it will then sort by those. And so I'm showing you an output from that. Here is, so this is actually from the process analyzer, but if I were to do this in the output analyzer, it would look a lot like this, where it would show you all your factor levels, and it could then highlight in red factor levels that it thinks are the best, but it can't tell a difference between. So this is saying that these two factor levels are probably better than this factor level, but I can't tell the difference between these at the 95% level. So that's how you read these plots. So then the process analyzer is another tool that we'll have a video online showing you how to use, and this greatly speeds up running these things. And then the OptQuest is I'll put another video online showing you how to use OptQuest, and that makes it much, much, much faster to choosing optimal parameters. So that's sort of a summary of everything you can do inside Arena to get these intervals. And there's not that much more in here. It's basically how to work with those half-widths. So if it's not clear, well, I may start with this stuff later. There's only 2 or 3 slides here. So we'll end with an attendance question here. And so the question here would be, if a confidence interval is a measure of error on my estimate for a point estimate, what interval, what is the name of the interval we use that captures the whole spread of the data? In other words, answers where does 95% of the data fall within? So confidence interval is really just a point estimate. What is the name of the interval we use that captures the whole spread of the data? And then that's all I've got for you today, so I'll see you next week.
What was the question?